multiplication. Okay? Multiplication. All right? And let's take a look at how we do this. We always start by breaking down the algorithm like we used to do it in grade school. So I'm going to come up and I'm going to perform multiplication on two decimal numbers. Okay? And let's say I had a 15 times a 15, okay, decimal. And I say to you, first of all, what are the names of these? Product. Everybody gets product. Product is the result. Okay. Multiplicand and multiplier. This is multiplicand, and this is multiplier. Okay? And you're like, well, I don't know if that's right. It's Lemire's 2016 compliments of Wikipedia. All right, so that's it. And let's think about the steps that I do to actually perform this multiplication. I am going to do the whole partial product and then add them all up. So what I'm going to do is I'm going to start with this little fella right there, and I'm going to take this least position symbol of the multiplier and multiply it up by that. So I'm going to get myself a what? It's like 75 or something like that. And then I'm going to come over here and I'm going to do this little puppy right here where I say, okay, I'm going to do the next higher order position and I'm going to multiply it so it comes out to be 1, 5. And then what I do is I go ahead and add them, but I had to make sure that I kept this little fella, like the product of this single term, in the right position. So then I come down here and I go, okay, I'm going to add 5 plus nothing is a 5er. 7 plus 5 is something like a 12er. And then I'm going to do a 2, and I end up with that. Okay? So that is what I did. That's the steps that I can do to perform this multiplication. And the reason we do that is just like addition, because we're going to build a circuit that will do almost the exact same thing, performing that exact same algorithm. All right? Now, the first thing I want to start with is how big does the product need to be in binary in order to hold all possible results? Okay? And we can do this by proving it to ourselves. Do you remember how many bits in addition the sum would ever be? If I had an n-bit adder, how big could the sum ever be? N plus 1. Okay? Life is good. Now I come to you and I say, how can we prove the multiplication thingamajig? Well, I could actually just say, how many bits does it take to do 15 and 15? Notice that we're back to our 4-bit example. So this is actually kind of the same as saying 1, 1, 1, 1, multiplied by 1, 1, 1, 1. And if we did this, why don't we do it this way? Let's perform the binary multiplication using the partial products and sums, and let's see how many bits we end up with. Because this would represent the highest possible multiplicand and the highest possible multiplier, and that would represent the highest possible product. So, here we go. I'm going to do it in red. Let's start with the least significant. Now, this is in binary now. So we're over in our binary, and I'm going to take this dude right here. Okay? And I'm going to come up here and I'm going to multiply it out. You know what's cool about binary? There's only 2 values. And when you're multiplying something by 1, it's just itself. When you multiply it by 0, what is it? 0. So I can come in here and I can say, okay, this is going to be 1, 1, 1, 1, bam. That was a partial product. Okay? Then let's come over to this position and do that guy. I'm going to go 1, 1, 1, 1. Notice how I had to shift it over. And then I come to this and you go 1, 1, 1, 1. And now what I want to do is I'm going to take all these, what I call partial products, and I'm going to add those puppies together. Okay? Now, when we do this, we also got to kind of remember, it's like these little gaps right here. It's like there's really nothing here. Notice how there's nothing here? That's fine. We just treat it as like adding to 0 or whatever. But I can just take 1, bring her on down, a boom. Okay? Then I'm going to go 1 plus 1 is what? 0 with a carry. And then I got, holy smokes, 1 plus 1 plus 1 plus 1. Now we're cooking. Holy, we've never done this one before. We added 2 bits together, easy. We added 3 bits together, made a full adder. This is the first time we have 1 plus 1 plus 1 plus 1. What is the answer? What do you think the answer is? 0 carry 1, 0. Yeah. That sounds weird. The way I kind of think about it is the answer is 4. right? But it's 4 in binary. So if you think about it, it's basically like 1, 0, 0, but you only get to keep the least significant guy. So what you do is the sum actually is 0, but then these 2 higher order bits are the carry. So that dude's going up to here. Boom, boom. So I actually carried a 1, 0 up there. How's that feel? Yeah. If you're not a 1, you're a 0, right? Brock Lemires. Okay. Now, I'm going to do 1, 0 plus 1, 1, 1, 1. Holy crap, what's that going to equal to? Can I just flip into decimal really quick? Okay, I know that is how many? It's 2, and then 3, 4, 5, 6. So what's that going to be? Well, that's going to be 1, 1, 0. I'll write it down here. So that's like 1, 1, 0. So I'm going to say this little fella right here, leave it. So I'm going to say the result is a 0, and I'm going to carry 1, 1. Okay? Then I'm going to go 1, 1 plus 1, 1, 1. What's that? Well, it's 3, 4, 5, 6 again. So it's actually 1, 1, 0 again. So I'm going to take the little buddy, the least significant, leave it. Now I'm going to carry this guy up here, 1, 1. And now I got 1, 1 plus 1 plus 1, which is what? So 1, 1 together is 3, 4, 5. So what does 5 look like? 5 is like 1, 0, 1. Is that right? Okay. So I'm going to take the little buddy, the least significant, drop her there, and then I carry a 1, 0 over there. And then I'm saying 1, 0, which is how many? 2, is it? Plus 1 is what? 3. All right. So I'm like, oh my God. Is that right? Yeah. So the answer is 3. So I leave my buddy here, the least significant. And what do I do with this guy? It like carries over into like who knows where. So what do I do with that last most significant bit? I just put it on the end. So there's nowhere to carry it, so I just put it right there. Okay, deep breath. How many bits did it result in? There's a nibble. There's a nibble. The answer is how many bits? 8. So we have proved to ourselves that an n-bit multiply results in a 2 times n product. Okay? Now, notice that the result, if you look at this result, this is 8 bits. What is the largest decimal value that an 8-bit code could take on? It would be 2 to the n minus 1 is equal to 255. So we could represent up to decimal 255 using 8 bits if they were all ones. But this is the highest number we would ever get to. And what is this number? Does anybody remember what this number is? The product? Yeah, it's 225. So this is actually 225. So we have a whole pile. We have 30 codes that we'll never use in this product. And is that okay? Yeah, bits are cheap these days. Okay? But it's just kind of interesting to know. All right? Now, if somebody came up to you and said, I'm going to have an 8-bit product, what's the highest value you could ever have? You don't immediately go, well, 8 bits can be 255. That's not correct. In a product, the highest it could ever be would be this little fella right there, 225. So we proved 2 things. 1, we know the maximum size of the product, and 2, life sucks. Would you agree with that? Look at this. This is ridiculous. We got numbers adding to numbers. I don't know about you guys. I like to simplify it. Okay? Going from a 2-bit adder to a 3-bit adder was hard enough. I am not going to build a 4-bit adder. Okay? I want to use what I have, which is a full adder. That means you can only ever have 3 inputs if we were going to build a circuit to do this. All right, so we kind of found a limitation of how to build our circuit that we got to keep in mind. But before we do that, let's start looking at the circuit. Okay? I want to create a circuit, and what I would really like to do is do some multiplication. We know we're going to have partial products, which means that you're going to multiply one of the lower bits, the multiplier, by the top thingamajig, which is the multiplicand. Say that fast. Multiplicand. Multiplicand. How come no one's saying it with me? That's fine. That's fine. I get it. Let's focus. Alabama? Is that what you said? Alabama?
Your accent sounds like deep south.
Oh, I didn't even know I had an accent.
No, when you say
Multiplican. Got my multiplican. Multiplican. Focus! All right, so I ask you the following. Let us create a logic circuit which will perform multiplication. So I come up to you, and I'm going to go back grade school, okay? 0 times 0 is what? 0. 0 times 1 is what? 0. 1 times 0 is what? 0. 1 times 1 is what? 1. Can anybody think of a gate that would do this for us? Yeah, AND gate. We perform multiplication with a 2-input AND gate. That's it. It actually is, it is that simple, okay? So what I want to do, though, is I want to break up my circuit in order to use products that are calculated on the individual bit level, okay? 2 inputs only, and then what I want to do is I want to add them together, but I only want to use an adder that has 3 inputs because that's what I've built, all right? So check the following out. I walk up to you and say, here is an agnostic looking little multiplier, okay? And the top will be A, the bottom will be B. They're 4 bits, so that means that we're going to have an 8-bit product. And I go to start building the circuit, and here's what I first do. Okay? Now I spread it out a little bit, but I'm going to take the bottom least position bit of the multiplier, which is going to be our buddy B. And we're going to multiply it by A3, A2, A1, and A0. We do that with 4 AND gates, and that's it. So if you look at this, I use the subscripts to denote it. Now what I'm doing is I'm drawing it out almost like a logic expression as opposed to an AND gate, just because I could, when I drew the AND gate, it would print it as like a dot. So I did it like this. Okay? Now I say to you, what am I going to do next? Well, let's go and let's get our next little pal, which is B1, and let's go ahead and multiply it by the entire multiplican. Okay? And then you know what we might want to do? Let's go ahead and since we now have 2 inputs, what if we started adding right away? Okay? So for example, if I wanted to do, come over here and I want to do 1 plus 1 plus 1 plus 1, and I want to do that, could I do it like this? Could I go 1 plus 1 and get a result, which would be whatever, 1, 0, and then do plus 1 and basically do the additions incrementally, okay? So we call that the partial sum. So what I'm going to do here is let's go ahead and let's pop some adders in there. We know that bit position 0 for the product is actually already done. If you look at this, check out what I did in order to get bit position 0. It's already done. There it is. It's down there. Can everybody see that? There it is. All I did is I took it and just popped it down there. But to get the next dude over, product position 1, what I had to do is I had to add these 2 partial products using a full adder, and I popped it down to here. Now wait a minute. A full adder has 3 inputs. So what do you do with that 3rd input that we don't use yet? You know what? Slap a little 0 on there. Okay? Now look at this. I've got this partial product, this partial product. I'm almost ready to roll, except now what I'm going to do, let's go ahead and get the next partial product, which is going to be using B2 as the bit of the multiplier. And it's multiplied by the entire multiplican. Okay? And now what I can do is do a little bit more addition and check out how this starts working. You look at this and you're like, okay, I see what you're doing. I needed to add this bit times plus this bit plus this bit. I just broke it into 2 adders, brought that sum down, and now I have product bit position 2. Isn't that sweet? And then you just do the exact same thing, booyah, 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 and you have now built an entire circuit. Now think about this. This is pretty awesome, if you ask me. I come to you and I say the following. 4 bits times 4 bits, how many 2-input AND gates did you use? 16. How'd you get that? Same way I did. I just counted them. Okay? Because each of these are nothing more than 2 input AND gates. Okay? So that's pretty sweet. And then the adders, look at how you have to track the carries as they flow through here. Okay? Because you have to, the carry going over to here really is a carry. Okay? It's the exact same thing that we did when we brought the carry over into the next position. So this is it. You could build this with basic gates on a breadboard, couldn't you? I don't think you could. Look how many gates are in here. Look at this. You already have 16 AND gates. 16 AND gates. And then look at what's in a full adder. Does anybody know what's in a full adder? At least 2 exclusive OR gates, at least 2 AND gates, and at least an OR gate. So you got 5 gates. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 times 5 is 60 plus 16. That's 76 gates in order to implement just that little dude. Okay? Oh! Isn't that awesome? Well, you're certainly not going to build it on a breadboard, but you could put it on like an FPGA, couldn't you? Couldn't you? All right. We always got to ask ourselves, that's a whole honking lot of logic. Do we ever concern ourselves with the delay? And it turns out the answer is absolutely. What you do with combinational logic delay is always look at the worst case path. You know what's crazy about the partial products? Do they all occur at the same time? Look at all the AND terms and say, do they depend on any interim calculations, or do they only depend on A and B? A and B. The product term in the multiplier is the first level of logic. In one level of logic, all the partial products are performed. Then what has to happen is that those results start going into the adders. And I draw this as a ripple carry adder because if you use a carry look ahead adder, it can get pretty monstrous, right? So if you look at this, the worst case delay through this is actually going to be level 1 will be right here, and then it'll be like level 2, level 3, level 4, level 5, level 6, level 7, level 8, level 9. And you go, wait a minute, level isn't even the right word, is it? It's like 9 chunks of delay, because each one of these is actually made up of multiple gates, isn't it? So you actually have, the way you calculate this is you say level 1 delay plus how many stages of a ripple carry adder. Do you remember the equation for the ripple carry adder? There it is. 3 plus 2 times n minus 1. Now this assumes that all the gate delay is the same. Okay? But if you look at that, there you go. All right. How many n is there? It's not 4, is it? Because we had 4 bits on the input, 8 bits on the product. So you were like, well, what's the n in the ripple carry adder? Probably how many full adders are in the chain? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so it is. It's 8. All right. How's that feel? Feel good? All right. Good. Glad we're all on the same page. All right. I got something cool to show you. As if that wasn't cool. Okay. As if that wasn't just frickin' awesome. I want to show you a little trick. What happens if you multiply by 2? Did you know that if you take a binary number and want to multiply it by 2, all you got to do is shift it to the left. You're like, wait a minute, what are you talking about? Check this out. I walk up to you, and I'm going to say, here's an arbitrary number, which is 1, 1, 1, 1, and that's equal to 15 decimal, unsigned. And I'm going to multiply it by 2. The result should be 30. All I'm going to do is I'm going to add a 0 to the least significant position and go shift, 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 shift. And now I look at that number, and I want to know what it is in decimal. Well, this position's worth 1. This is worth 2. This is worth 4. This is worth 8. This is worth 16. 16 plus 8 is 24. Plus 4 is 28. Plus 2 is equal to 30. That dude right there is equal to 30. How frickin' cool is that? Multiply by 2, shift left. Okay? Now, it's not just a shift. it's shift and pad it with a 0, okay? And do you know what that, I can never remember it either, I just look in the book, but there's arithmetic shift and then there's logical shift. Logical shift is actually the one which pumps in a 0, okay? And you can keep doing this as much as you want to a point. So here's an example. Well, let's say that I had 15 like I did, and I multiplied it by 2 by shifting left logically. That got me to 30. Then I shift left again. That got me to 60. How awesome is this? Here's the trick though. How long can you do this? Until you run out of bits. Okay? So you got to make sure you know what the maximum range is of your product. So if you have a 4-bit number and your product is going to be 8 bits and you know you're going to multiply by 2, you can multiply by 2, multiply by 4, multiply by 8. But if you ever have a result that is larger than the largest value you can contain, you're screwed. Okay? But it is a very quick and easy way to multiply by 2. How's that feel? All right, all right. Let me ask you a question. Okay, I just want to ask you a question. What do we do if we have a signed number? Now we're going to multiply by a signed number. What in the world are we going to do? Well, let's think about this. Okay, I go 7 times 7. What's the answer? In decimal. 49. Okay, I go 7 times negative 7. What's the answer? Negative 49. And if I go negative 7 times negative 7, what's the answer to that? It's 49. Okay? Now here's what's interesting about this. If I came in and did this multiplication using binary, I would just simply have 0, 1, 1, 1, 0, 1, 1, 1, and it would absolutely indeed come out to be 49. Okay? Using our algorithm. If I did this guy, what I would end up having is I'd have 0, 1, 1, 1 multiplied by, how do I represent a negative 7? I got to do a 2's complement code. What was it? Did you know it? 1, 0, 0, 1. Do you think that those two inputs will result in the same output? No. The answer is no. Okay? So here's what we do. We always build an unsigned multiplier. We always build this guy. Then we do the signs exactly like we do with the human brain. We just apply them afterwards. So there's actually, when you do multipliers and you're going to handle signed numbers, you have a first stage which first checks, is the number positive? If it is, life is good. If it is negative, you know what you have to do to it? Flip it to positive so that our multiplier will work, and then save the sign. Okay? Same thing over here. We have negative 7 and negative 7. This is going to be 1001 times 1001. This is going to give us yet another wrong answer. So what we have to do is first convert that using 2's comp, convert that with 2's comp, and track how many times we had to do it and give the sign accordingly. So in this situation, every time I perform 2's comp, I said, oh, I flipped the sign to a negative. Then I perform it again, flip, I go back to the other way. Okay? All right, pretty sweet, pretty sweet.